This is the first lecture on Chapter 7, and 7-1 starts with confidence intervals for the mean when sigma is known. Chapter 7 is the first chapter of the next part of the statistics, which is inferential statistics. Inferential statistics will allow us to estimate the population parameters given sample statistics. So what we need to start with is the idea of what's called a confidence interval. And what we're using is we're using a normal distribution. We're allowed to use normal distribution because of the central limit theorem. The central limit theorem allows us to gather information from a sample and treat it as a sample, therefore part of the sampling distribution. Therefore, I can use the normal curve. And if I would like to identify a 95% confidence, what I'm actually referring to is the middle 95%. So if in the middle of my normal curve is my mu, I want to be 95% sure that the x bar is somewhere in the body of the problem. So what we do is we look at this as, we're going to label these as z alpha over 2, and then you're going to find out in throughout the chapter why it's labeled this way. This is going to be a negative value, this is going to be a positive value, and what it'll cut off is the placement of the 95%, the middle 95% on the normal curve. In order to look up these values, all we're doing is identifying the area to the left, and we can use our calculator under an inverse norm and be able to look up these items, these numbers. So notice, if I have a 95% in the middle, that does leave me with 5% that have to be split up equally into two tails. So these little pieces that sort of come off on the sides, they're called tails of the distribution. So if I have 5% that needs to be split up into two pieces, that leaves about 2.5% on each side. So I know that this area is 0.025, that's 2.5%, and on the other side I have 0.025. Now in order for me to look up the leftmost z, I can type in inverse norm 0.025 for my area, and then all I'm looking at is the standard normal distribution, so I have 0, 1, and this will give me a 1.96. Now this one's going to come out to be negative, so on this side, with a 95% confidence interval, the leftmost z is a negative 195. If I use symmetry on the other side, this is going to be 1.96 positive. So looking up the z-scores that we're interested in is something that you can easily do with a calculator or with a list of the z-values that are most useful for this book. So that's not the problem. The problem is to actually be able to go through the math and correctly place all of the pieces together. So I'm going to start with assumptions, and you'll find that the assumptions will be very similar throughout the whole chapter 7. I need to have a sample. I need a sample to be a random sample. I need to have either n is greater than or equal to either n is greater than or equal to 30, or population normally distributed. And notice I don't need the original population to be normally distributed. I only need it if I didn't gather a sample that's large enough. So when n is greater than or equal to 30, I can actually use this if it's a good enough sample, and that's according to the central limit theorem. And here's the formula. So the formulas, you'll notice that right around chapter 7, these will get intense, and this is what the calculator is for. So I will explain the meaning of this formula and go through the example in this video. In the next video, I will show you how to use your calculator so that everything comes out much faster. So what we're trying to do is we're trying to estimate a mu. The way we will estimate it is through the interval. So meaning the mu is a little bit greater, or it's greater than one value and it's less than the other value on the other side. So let's start with this one. The mu is going to be less than the x bar. So the x bar is going to be called a point estimate, and I'll label these in a second. And what I need to do is I need to add a margin of error. So the margin of error is calculated by taking that z alpha over 2 score and multiplying by sigma over the square root of n, which is something that we've seen as part of the central limit theorem. So on the other side, I have the same thing, but with a minus. So you start out as x bar because that's the best estimate for your mean. You take a sample and then you find the mean of that sample. So that's your best estimate. And then you subtract that error. So subtracting an error will give you a lower bound. Adding an error will give you an upper bound. So let's label these. The x bar is going to be called point estimate. This is your first jumping start. These are your vocabulary words. Your z alpha over 2 is called critical value. It's the z that is being cut off by in the standard normal distribution. The whole interval is going to be called confidence interval. What we're going to be using is we're going to be using 95% confidence, 90% confidence, and 99% confidence. Now, it's not because those are the only confidences that you can use. It's that this book is only using 95, 90, and then 99 because the table that is provided by this book is very limited to what is. So the book is limited by the values that are in the table. In reality, you can pick any confidence you'd like, but we'll stick with the 3 that are most common. Now there is a z score that corresponds to each of these. So 95% confidence, you can use 1.96. The 90% confidence, the book uses 1.65, but I'd prefer 1.645 because that would be a better estimate. And a 99% confidence, the book uses 2.58, but I think that one's a little bit off as well. So these ones are called confidence level. One more piece. This piece of the formula is called margin of error. It is also referred to as maximum error of estimate. And what we should do next is an example. So what I have done is I actually typed up an example. So those of you who aren't holding a book with you at this particular moment, which I was under assumption that you did in the previous chapters. So I've typed up all of the examples in here. This is a 7-1 example. And what it says is a researcher wishes to estimate the number of days it takes an automobile dealer to sell a Chevrolet Aveo. A random sample of 50 cars had a mean time on the dealer's lot of 54 days. Assume that the population standard deviation is 6 days. Find the best point estimate of the population mean and the 95% confidence interval of the population. So what we're trying to do is we have gathered a sample. It is very important to label it correctly. So I'm going to highlight things and start labeling in a second. And we're trying to plug it into this formula. Except the formula is programmed into your calculator. So what we're going to be doing is we need to locate what exactly is that the information that they have given us and what the button is called. So that's what we're doing right now. So let me read this again. A researcher wishes to estimate the number of days it takes. Okay, so this is again a random sample of 50 cars. So I'm going to highlight this number. If it's a random sample, I'm going to give it a letter that represents a random sample. So those of you, I'm going to bring this up for a second. Those of you who are going to try to use this formula, you now have a number for your bottom piece, which is an N. Now the sample had a mean time of 54 days. So the 54 days that they gave me is a sample of the mean. So given a sample of the mean, let me give one more piece of information. Assume the population standard deviation is 6 days. So this is another piece that they give me. Sigma is equal to 6. And what they're looking for is a 95% confidence. Okay. Now the best point estimate is the X bar. So if you're trying to estimate the number of days that the automobile is going to be on the dealership, well, you gathered a random sample and your sample showed 54. Well, one sample is great, but can you predict what happens for all of the samples? So this is what this is for. It's the first prediction. So our point estimate is going to be 54. And what you want to do is you want to add error. Now, 95% uses 1.96, and then 6 over the square root of 50 goes exactly right there. Now, this is where the mu is stuck, and 54 then minus 1.96, and then 6 over the square root of 50 on the other side. You can go ahead and plug this into your calculator. What we're doing is, given some information about the sample, we're predicting the population parameter, the mu in this case. I'm going to stop the video at this point because what I want to do is I want to switch over to a calculator.